Have you ever wondered what's happening inside the mind of an AI when you ask it a question? What if I told you that even the researchers who built the powerful AI systems don't fully understand how they work? It's like having doctors prescribe medications without knowing how they affect your body. In this video, I'm going to take you inside the fascinating new research that's creating microscopes for AI systems. It's allowing us to peer inside these black boxes and discover surprising mechanisms that might just change everything we thought we knew about artificial intelligence. I'm Evan Goldstein. I'm a licensed professional engineer and a data scientist. I'm building AI Capitalist to talk to the leaders and the thinkers, like you, about navigating this brave new world of thinking machines. When you ask ChatGPT or Claude to write you a poem or to explain quantum physics, there's an incredible amount of computation happening behind the scenes. But despite creating these powerful AI systems that can write essays and debug code and even create art, researchers often don't fully understand how they work internally. This is like building a brain without knowing how it thinks. Shocking reality of modern artificial intelligence. This opacity becomes even more concerning as we increasingly deploy AI systems in critical applications like healthcare and finance and legal settings. Would you trust a doctor who couldn't explain their diagnosis? Or a judge who just couldn't articulate their reasoning? Yet we're rushing to integrate AI into these fields without fully understanding their inner workings or mechanism. That's exactly what researchers at Anthropic are tackling with their groundbreaking new paper, Biology, revealing computational graphs in language models. They're developing methods to peer inside these black boxes and to understand what's actually happening when the AI generates text. It's like they're creating microscopes for AI, which is allowing us to see the invisible machinery that powers these systems. So what exactly happens inside a large language model when it answers a question? When an AI like Claude contemplates the sentence, "The capital of Texas is," with Austin, what internal steps did it take to arrive at the right answer? Did it just memorize the fact? Or did it reason through intermediate steps? First identifying Texas as a state, and then recalling that Austin is its capital. These questions arise because modern language models are incredibly complex. They contain billions of parameters, and they're arranged in intricate networks. The researchers draw a fascinating parallel to biology. Understanding language models is similar to the challenges that biologists face when they're studying living organisms. Just as living creatures have evolved complex mechanisms over billions of years, language models develop sophisticated computational strategies during training that aren't directly programmed by humans. Before the invention of the microscope, the inner workings of living organisms was pretty mysterious. Similarly, until now, we could observe what language models output, but not how they arrive at those outputs. The researchers realized they needed new tools, their own version of the microscope, to examine these AI systems and identify the building blocks of model computation. So to peek inside the black box, the researchers at Anthropic developed a methodology that they call attribution graphs. Think of a language model like Claude as an incredibly complex machine with millions of interconnected parts, like artificial neurons. It's too complicated to understand directly, so researchers first create a simpler and more interpretable version that they call a replacement model. As you can see in figure 1, the researchers replace the original model's neurons with more interpretable features that often represent human understandable concepts. This is similar to how biologists might create a simplified model of a cell to study specific processes. The simplified model doesn't capture everything, but it's designed to be easier to understand while still preserving key behaviors. The researchers use what they call a cross-layer transcoder to build this replacement model, which translates the complex activations of the original model into more interpretable patterns. They also add error nodes to represent the parts of computation they can't interpret cleanly. Now, once they have this more interpretable replacement model, the researchers compute attribution graphs that show how information flows through the model for a specific prompt. Think of an attribution graph as a map showing the journey of ideas through the model's mind, and it shows which features activate, how they influence the other features, and ultimately, how they lead to the model's output. For example, in one of their key experiments, they analyzed how Claude completes the prompt, "Fact, the capital of the state of containing Dallas is ... The attribution graph reveals fascinating insights. So let's look at figure 5 and 6. Here we can see how the model first activates. So here in figure 5, we can see how the model first activates features representing Dallas, which then activates features representing Texas, which in turn activate features representing Austin as its capital. This visualization is showing us a genuine multi-step reasoning that's happening inside of the AI. The researchers could verify this through intervention experiments. So here we see a variety of different paths that the AI used to get to the answer Austin. So these researchers could verify this through intervention experiments that are shown here in figure 7. In these experiments, they modify the activations of specific features and they observe how this affects other features in the model's outputs. For example, they inhibited the Dallas features, and that decreases the activation of Texas features, and it changes the model's output to other state capitals. So you see on the bottom corner here, when that is depressed, when the word Dallas is depressed, now it's spitting out Albany, Springfield, and Sacramento. Those are capitals of other states because Dallas has been suppressed. This is confirming that the computational paths identified in the attribution graphs genuinely reflect causal mechanisms inside the model. Figure 9 shows even more powerful evidence. When they swap Texas features for California features within the model's internal representation, the model outbursts Sacramento instead of Austin. When they swap in Georgia features, it outputs Atlanta. These intervention experiments are demonstrating that the model is genuinely using these internal representations to determine its answer. In another fascinating case study, they examined how Claude writes rhyming poetry. You might think that the model would just improvise line by line. So you can watch, I sort of voiced over a video that Claude put out to explain this in my own words.
You often hear that AI is like a black box. Words go in and words come out, but nobody knows why it said what it said. And that's because AIs aren't programmed, they're trained. And during training, they learn their own strategies to solve problems. If people want AIs to be as useful and reliable and as secure as possible, then someone's got to open up that black box and understand why they do the things they do. But even opening the black box isn't very helpful because outsiders don't know how to interpret the things that they see going on. Think of it like a neuroscientist investigating the brain. They need tools to work out what's going on inside. They want to know how the model connects all the concepts in its mind and then uses them to answer the questions it's being asked. They can actually see how these concepts are connected to form logical circuits. So we're going to look at a simple example where the Claude researchers asked Claude to write a second line of a poem. The poem starts, "He saw a carrot and had to grab it." In Anthropic's study, they found that Claude is planning a rhyme even before writing the beginning of the line. Claude sees a carrot and grab it and thinks of rabbit as a word that would make sense with carrot and rhyme with grab it. Then it writes the rest of the line. His hunger was like a starving rabbit. They look at the place that the model was thinking about the word rabbit, and they see other ideas that it had for places to take the poem. They also see the word habit is present there. Anthropic's new models allow them to go in and intervene on this circuit. In this case, they dampen down rabbit as the model is planning the second line of the poem, and they ask Claude to complete the line again. His hunger was like a powerful habit. They see that the model is capable of taking the beginning of a new poem and thinking of different ways it could complete the poem and then writing it towards those completions. The fact that they can use these changes to occur well before the final line is written is strong evidence that the model is planning ahead of time. This poetry planning result, along with many other examples in the paper, only makes sense in a world where the models are really thinking in their own way about what they say. Just as neuroscience helps doctors treat diseases to make people healthier, Anthropic's longer-term plan is to use this deeper understanding of AI to make these models more safe and reliable. If they can learn to read the model's mind, they can be much more confident in doing what they intended.
And what the researchers are finding is that the model often plans ahead, and it activates features corresponding to potential rhyming words. So if we're looking at figure 25, it shows the operand plots for different addition features. Now, this is a case where the model was asked to perform a simple addition problem. The model uses multiple parallel pathways, and it combines rough estimation with precise calculation of the ones digit. This is showing that AI systems are developing their own unique cognitive strategies that are different from human approaches. Think about the standard stacking algorithm, as they call it, where let's say you did 11 plus 12, you would do 1, 1 plus 1, 2, and then you would add the ones, get 3, add the tens column, get 2, and you get 23, right? In this case, what it's actually doing is sort of homing in on the value by estimating in different ways. But here's the key. When it answers, when Claude was prompted as to how it got the answer, it went through the regular algorithm and it explained it to the user as if it had used the standard stacking algorithm. So it's not really telling you what it's actually doing. It's telling you what it thinks you want to hear in a way. The ability to peer inside AI systems and to understand how they work has profound implications for all of us. Think of AI like a car. Most of us use cars daily without understanding exactly how the engine works, and that's fine for normal driving. But what if your car started making unusual decisions, like sometimes turning left when you steer right? Suddenly, understanding the mechanism becomes crucial for safety and reliability. And if you're getting value from this content, I would appreciate it if you'd push the like button. Pressing like lets me know that I'm making content you want to see, and it spreads that content to others. Let's break AI capitalist out of small channel hell together. Similar to this, AI systems become more integrated into our daily lives, and now they're making decisions in healthcare and finance and education and more. So understanding their internal mechanisms is much more important. The methods developed in this paper could help medical professionals verify that an AI is using medically valid reasoning rather than spurious correlations. For example, in a medical case study from the paper, it shows how Claude reasons through a diagnosis by activating features related to symptoms, possible conditions, and appropriate follow-up questions. In the case of a pregnant woman with concerning symptoms, they found that the model internally represented concepts related to preeclampsia, which is a dangerous pregnancy complication, even though the term wasn't mentioned in the prompt. So for example, in a medical case study from the paper, Figure 30 shows how Claude reasons through a diagnosis by activating features related to symptoms and possible conditions and appropriate follow-up questions. In the case of a pregnant woman with concerning symptoms, they found that the model internally represented concepts related to preeclampsia, which is a dangerous pregnancy condition, even though the term wasn't mentioned within the prompt itself. And then here's a mapping of sort of how the concepts moved through the model. And here in Figure 31, it's showing what happens when they inhibit the model's internal representation of preeclampsia. The model is switching to suggesting symptoms related to other diagnoses. This is suggesting that the model is genuinely reasoning about potential diagnoses internally. These methods could also help identify when models are using flawed reasoning. For example, when researchers examined how Claude handles questions about unknown people, like which sport does Michael Batkin play, they discovered a fascinating mechanism, which is shown here in Figure 33. So the paper from Anthropic presents a very big advancement in AI interpretability, but it's important to consider its limitations and how the broader research community is responding to this. The researchers themselves are candid about the limitations of their approach. They say that their attribution graphs provide satisfying insight for only about a quarter of the prompts that they tried. It means that 75% of cases showed methodology that either doesn't work well or it provides incomplete explanations. And they stated in the paper, like any microscope, our tools are limited in what they can see. This is a crucial acknowledgement. While the method provides valuable insights, it's far from a complete solution to AI interpretability. One major limitation is that their method doesn't capture how attention mechanisms work in transformer models. Attention is a big component that determines how information flows between different parts of the input. But the attribution graphs treat attention as a black box. This is a significant blind spot because a lot of complex behaviors and language models are big on attention.